Hello, Algebra 2 folks, and welcome to Exponential Growth and Decay. Again, we're talking about growth and decay, but today we're going to do real-world examples. And let's talk about the money. Anyway, so you need your guided notes and a pencil and a calculator, and we will get started. All right, example number 1 is talking about compound interest. This is an example of exponential growth. We talked about that yesterday. We use this model when we're not compounding interest on a yearly basis. So when we're talking about it being compounded monthly or semi-annually or quarterly, we would use this equation. All right, so A is equal to P parentheses 1 plus R divided by N, all to the power of N times T. So P is your initial amount deposited. So if you have $500 and you want to put it in the bank, that's the amount that you would deposit right away. Your initial amount. R is the interest rate, okay? And that is always expressed as a decimal. So if I have, 4.5% interest, yes, that's a decimal and a percent. But interest rate expressed as a decimal, we would take our rate, if we have a percent, and we divide it by 100, so it'd be 0.045. Okay, so just remember the rate is always divided by 100. Okay, and then N is the number of times it's compounded per year. So when you get your bank statement, it should tell you how it's compounded. If it's semi-annually, that means you are getting interest compounded twice a year. So that would be a 2. If it's quarterly, you're getting interest compounded 4 times a year. If it's monthly, it's 12 times a year. If it's weekly, it's 52 times a year, because there's 52 weeks in a year. If it's daily, it's 365 times a year. So your N depends on how much your bank is compounding your interest. Now, if it's compounding it annually, once a year, yearly, N would be 1. And then we wouldn't need to use this formula. We would use the next formula that I'm going to talk about. But most banks use these these 5 types of interest rates, compounding. T is the number of years you want to let it sit in your bank account. And A is your balance after you let it sit in your bank account. Okay? So we're going to go ahead and use that formula to figure out how much money we would make. So we deposit $2,900 into a bank account. Okay, that's our initial amount. A is what we want to find. 1 plus the rate is 0.035 because you take 3.5 and you divide it by 100. And then the number of times that it's going to be compounded. Yes, I know it says annual interest, but the word compounded is what we're looking for. If it's compounded yearly, we would put a 1 here. But this is compounded monthly, so we're going to put a 12 here. And then it's to the power of N, so that's 12, times the number of years you are going to keep it in your bank account, which is 2. And then you're going to type this in your calculator, 2,900 parentheses 1 plus 0.035 divided by 12, and all of that to the power of 24. I'm just going to do 24, otherwise you need to use parentheses around the 2 times the 12. And we are going to get an ending value of $3,109.96. So $3,109.96. Okay. Now, if we have exponential growth models that don't include interest and interest being compounded, then we would use this model. Now, this is our growth factor, okay? So when we were doing our graphs, we called that B, okay? So in our growth graphs, it was this. Okay, that's what we used the other day when we were graphing. Well, all we're doing is changing this B to 1 plus R, because when we use these real-life models, we are given a rate, and we have to add that to 1 to get the B, okay? So that's why we don't use the B anymore. We're using 1 plus R, because we got to figure out what that growth model or what that growth factor is, okay? So again, this time we have a little a, so it's y equals little a, parentheses 1 plus R, all to the power of t. Little a is the initial amount, the amount you start with. Okay, R is the percent, and then that's the percent increase. How much are we getting, or how much is it increasing by? But it needs to also be expressed by a decimal, so you have to take your percent divided by 100, and t is your time. And now all of 1 plus R is the growth factor. Okay, so let's go ahead and talk about an example using that formula. So population is an example of growth, exponential growth. It can be decay, but this one is growth. And when I'm reading the story problem, I'm going to be looking for words like growth, increased, went up by, appreciated. You know, I'm looking for words that mean go up, okay? So there's an initial population of 38 buffalo. Okay, well, 38 is our initial population, okay? And the population is growing 10% each decade. Oh, that's kind of tricky. 7% each decade. So 1 plus 0.07, because I need my rate in out of percent and in decimal form. So I took that and divided it by 100. Each decade. Okay, write an exponential growth model that estimates how many buffalo are in the park after 70 years. Now, many of you want to put 70 years here, but I'm talking about a growth per decade. And a decade is equal to 10 years. So how many decades are happening in 70 years? Well, that's 7 decades, because 70 divided by 10 would be 7 decades. So now I'm going to put that in my calculator. 38 parentheses 1 plus 0.07 to the power of 7. And I'm going to get 61.02. Well, guess, oops. Yep, 61.02. But oops, I can't have part of a buffalo. So when you are giving your answers, you got to think, when can I go to the nearest tenth? When can I go to the nearest hundredth? When is that appropriate? It's not appropriate to talk about part of a buffalo. So we're going to round to the nearest whole. So we would say 61 buffalo. Now, if we were talking about money, we could certainly say to the nearest hundredth, because money goes to the nearest hundredth. So think about what seems appropriate. Okay, well, now we're going to talk about the decay model and what you would use with the decay model. Well, this is the equation. It looks almost like the other one. But because we're talking about decay, we're going to talk about decreasing our value or losing the value. So the money is going to go down. So again, this looks a lot like the original one when you talked about that yesterday, A times B. But now B, when I take 1 minus R, my B now is my decay factor. And when I'm graphing, I'm given the decay factor. But in real world, you have to find the decay factor. So you have to take 1 minus the percent that it's decreasing by. So again, little a is the initial amount. R is the percent decrease, decrease, decline, depreciate, goes down. Those are the words you're looking for when we are doing real world examples. And that's expressed by decimal as well, dividing that by 100 again. I know I reiterate that, but that's where a lot of people make a mistake, so that's why I say that. T is time, and so then again, R minus 1 is your decay factor. All together, once you find that together, that would be called your decay factor. Okay, let's go ahead and do an example. So depreciation is an example of exponential decay. Depreciate, going down, okay? A new car costs $25,000, and that value of that car decreases by 23.5% each year. Okay, let's write an exponential decay model and then estimate that value after 4 years. Okay, so 25,000 is how much I spent, cold hard cash, buying that car. The first year, it loses 23.5%. In decimal form, that's 0.235, okay? And to the power of t. So I'm writing a model based on the power of t, okay, after t years. Now it says estimate it after 4 years. So how much would that car be worth in 4 years? All right, so if we plug that into our calculator, 25,000 parentheses 1 minus 0.235 to the power of 4. Oh my goodness, after 4 years, that car is only worth $8,562.21. Whew, that's not worth a lot. That's a lot of money to be spending after 4 years for not getting a lot of value. Now, I realize that not every car has that depreciation value. What you also need to know is that some cars have a lower depreciation value, like trucks and like Suburbans. They don't depreciate quite as much as like maybe a regular car. You also need to know that classic cars appreciate, which means they make money. They're worth a lot of money, okay? So some cars depreciate, some cars appreciate. And they all depreciate and appreciate at the different rates. So make sure you're reading those notes and making sure you're looking for those keywords. That's all, folks. We'll see you, and hopefully you're ready to practice some of these up. Have a great day.